so your group really describes studying microbial glues, enzymes, and redwood. So if a friend asked you what you actually do all day, how would you explain it simply?
Yes, and that list of measurements is constantly evolving. I was really taught early on in my career to be problem oriented rather than method oriented. And I think that's really important as a scientist, not just to get stuck to a fancy piece of equipment that we have in our lab or things like that. And so I was trained, as I say, when I want to scare somebody away, if I'm sitting next to them on an airplane, I was trained as a soil biogeochemist. And that word right across biology, geology, or physics and chemistry is my background. And also I'm a soil ecologist. But to answer your question, I think the way I would describe myself, and it's really evolved, especially over the last decade, is that I'm a soil engineer. I think very much like an engineer now because I work with land managers, ranging from farmers to ranchers to the Department of Environmental Quality. We might talk a little bit about dust later. And I try to understand their end goals, right? What their outcome is, what they're looking for. So much like an engineer, right? What is the ultimate goal? So I work across soil physics, chemistry, biology, sometimes combinations of those different disciplines. And then I go back to my toolbox and try to understand, okay, what solutions is it biology that could help the most? And really, it's a problem solving exercise to engineer a soil that functions more effectively for whatever that end goal is.
Yeah, so you grew up in Richmond and then you headed west for your PhD. So what made you stay with these desert soils instead of going back to somewhere greener?
Yeah, great question. I'm officially a desert rat now. I was really, I think, attracted to the Western US. I moved from Virginia out to Northern Arizona University and then was in California a while before I ended up here in Tucson. And I think what really resonated with the West in general for me was the wide open spaces. Now, whenever I go back to the East, I feel a little bit claustrophobic. And I think that I love trees, I always appreciate it, but there's something about the wide open spaces that is really, at a really fundamental level, personally has allowed me to think better and been more creative in a lot of ways. And on the more practical, that's almost more the like spiritual side of things and just how it's affected my psyche. I think at a more practical level, here in the Western, especially in the desert, you can see the soil a lot easier, right? There aren't those pesky plants to get in the way. And I'm saying that jokingly because we really need those plants, but I think it's been an opportunity to, because we have such more bare soil, there's a lot more problems that come along with that, such as dust pollution and and other issues related to that balance between plants and soils. And honestly, it's a bigger challenge in a lot of ways because of we're really the canary in the coal mine here in the southwestern US with heat and water scarcity and things like soil salinity or salinization of soils as well.
Yeah, so your lab, we're going to talk a little bit about the dust that you were talking about. Your lab studies the glues microbes make that hold the soil together and prevent erosion. And Arizona obviously is pretty common dust storms. So what exactly is that glue and what's happened once it's gone?
So the technical term for these glues is extracellular substances, or EPS for short. And if we unpack that, extracellular meaning that these are substances that, in particular bacterial cells, but also fungi and plants as well, release these substances into the soil environment. They polymeric, meaning that there's long chains, sometimes of just polysaccharide chains, but they can also have lipids besides carbohydrates. And these substances have evolved over millions of years to be particularly effective in holding on to water. So they're hygroscopic or water retaining substances. They also act like glues, as you mentioned. So they are really effective at binding soil particles together. And then it's even been shown that as soils dry out, these substances stay wet and can actually act as highways for nutrients to diffuse in soils across air gaps. So they're really effective at really connecting soils that become disconnected due to drying out in more air spaces. So they are a evolutionary adaptation to desiccation, so to drying out, but also to stabilize their environment. So that's one of the biggest disturbances to soil is water. As especially when you get big rainstorms, it really can mess up soil structure, obviously cause erosion and things like that. So these EPS molecules help stabilize soil structure around these both plants and microbes. When they're gone, so what happens when they're gone? Honestly, I don't know in terms of how important. So we've done some testing, for example, between Tucson and Phoenix. We did a really extensive survey of, we measured dust emission every 500 feet along this highway that is known to get really dusty. And we didn't find a good correlation between soil EPS concentrations and dust emission. What was actually more important is things like surface roughness of the soil. And so EPS clearly play a role at the micro scale, but it's unclear right now. I'd say the science is yet to be determined how important loss of EPS is, at least for dust emission.
Yeah, so something that a lot of people have stepped on without knowing. So what's really living in that crust, and why is breaking it matter so much?
So biological soil crust has been an interest of mine for a long time, even before I was a scientist. And for example, made trips out to Utah as a kid. And, you see these signs like don't bust the crust, right? As you mentioned. And that they can be certain types of biocrust or biological soil crusts can take a really long time to form. And so these are basically an assemblage of different organisms, including cyanobacteria, mosses, and then many more. There's a whole, you can think of these as a micro ecosystem. There's micro and macrofauna that are also associated with these biocrusts. In terms of why they matter, is that because of water limitation and arid environments, there's naturally going to be spaces between plants. There's not enough water to have, right, continuous plant cover when you're getting less than, say, 10 inches of rain a year. So these are ecosystems, microbes between plants, and they've been shown to definitely help with erosion. So you can actually take a crust. Oftentimes we'll use paint scrapers. You can literally like scrape off, there may be about a quarter of an inch thick, and put them in water, in a glass of water, and they'll stay together. They're really well aggregated, they're water stable. And so there's definitely a role in erosion. And then they also matter because they have a lot of nitrogen fixing organisms in them, including like an algae. And it's been shown at a global scale that biocrusts play an important role in fixing nitrogen in the atmosphere and putting it into a plant available form in the soil. So it's basically acting as a fertilizer.
Yeah, so I saw a paper from your group finding that irrigation increased both inorganic and organic carbon in arid cropland soils. That kind of changes the assumption that desert farming only really depletes. So what's actually happening there?
The nuance of that was led by my former postdoc Kirsten Ball. Really, we were comparing flood irrigation, which is used in a majority of the croplands, at least in, say, Arizona and Southern California. It's also known as furrow irrigation, where you're basically running water all the way across the field in basically ditches. We found that flood irrigation tended to favor inorganic carbon, which are various forms of carbonates, whereas drip irrigation tended to favor organic carbon accumulation. So if you're looking at total carbon, which is often measured in places like the Midwestern US or Eastern US, where you don't tend to have a lot of carbonates. Whereas in our soils, we can have a 1-to-1 ratio, just as much inorganic carbon as organic carbon. What I think is going on to focus on drip irrigation, increasing organic carbon, is the mechanism that we haven't nailed down yet, but our hypothesis is that inorganic carbon doesn't leach out calcium like is done with flood irrigation. So when you add flood irrigation, you get a lot of leaching of calcium. And calcium is known to play an important role in stabilizing organic carbon in arid systems. So it could simply be that because drip irrigation is not leaching out the organic carbon like flood irrigation, is that it's helping to keep that calcium near the organic carbon that's coming in from crop residues and so forth. So there's clearly there's pros and cons to flood versus drip irrigation. The reason that drip irrigation in general hasn't caught on in the desert Southwest is because even more important than organic carbon are salts. And we really need that flood irrigation, at least currently, to push those salts, to leach the salts out of the soil profile so that you can grow relatively salt sensitive vegetables.
Yeah, so there's a lot of enthusiasm about soil as a place to store carbon. So what can dryland soils realistically do, and where does the hype outrun all of the evidence that there's?
Yes, and there is a lot of hype out there. I'll definitely admit that. Really, I don't have a lot of hope in irrigated drylands to store organic carbon in the long term. It's hard even from season to season to increase organic carbon in these systems, let alone decade to decade. The reason for that is because these are often warm or hot ecosystems and they're irrigated, so they're wet. And that's ideal conditions for decomposition, for microbial decomposition. So where I have more, I think what's more promising and where I have more hope is in degraded arid grazing lands or range that, and by degraded, I mean that they've lost a lot of their plant cover, perhaps from historical overgrazing of livestock or for other reasons, there's been a change in the amount of bare ground. And I work with a colleague here at the US Geological Survey. We're actually just getting ready to do another sampling campaign this year where I think a lot of the solution is about slowing down water. So we tend to, this is actually our monsoon season right now where we get intense rains. When there are thunderstorms, you can get an inch or two in an hour, and we have really high rates of erosion. Where I see potential to store more carbon is to slow down the water. So often using indigenous practices that there's structures called media luna where you actually in these really eroded areas you put in rocks to sort of slow down the water or other natural infrastructure, check dams. And I think if we can capture that sediment and sort of bury that organic carbon before, that's where I tend to have more hope. The other is uh, using mulch, believe it or not. I had a former graduate student where we just took mesquite trees, which are common in these semi-arid, and just laying out branches of mesquite trees really changes the amount of erosion and allows native plants to reestablish easier than on bare ground.
Yeah, so, Rivka Fidel, she's the one who pointed me to you. So if you two were asked what soil health actually means, where do you think your answers would differ?
Well, I'd have to speculate a bit. I think that because Rivka's been in the southwestern U.S. for a while, I think we've gotten a lot of reality checks because I know, for example, she came from Iowa, I came from Virginia, and there's a lot of the science of soil health has been developed in the Midwestern U.S. and Eastern U.S. For example, there's a Cornell University soil health assessment framework. The Soil Health Institute is based in North Carolina, and they have great intentions. I'm a full supporter of their work. However, we have these different soils, different environments in the southwestern U.S. And I think that there are some missing indicators. If you look at those soil health assessments, oftentimes they don't mention like carbonates that we talked about earlier, inorganic carbon. Um, we have a lot of issues with sodium, or in particular, sodium adsorption ratio, which is the relative proportion of sodium to calcium and magnesium. And that can be a really important indicator, not only of sodium toxicity to plants, but also sodium is a basically causes soil structure to break down. So those are examples, I think, of where some of the biggest differences are. I should also mention that we deal with pHs, soil pHs in the 8 to 9.5 range. And so those are very different constraints on nutrient availability and how to manage soil health. The final thing I'll mention is that the soil health community focuses a lot on cover crops and continuous live roots in the soil. However, in order to do that in the systems, in the agricultural systems where I work, that requires even more water use because our cover crops are not during the winter, they're during the summer, this time of year, like June, July, August. And that is when it can be 120 degrees Fahrenheit. And cover crops, again, require even more water and therefore also more salt addition to the soil because our irrigation water comes from the Colorado River, which has a high salt content. So I think those are some of the contrasts. We're trying to figure out both what are the missing indicators of soil health and then also what are sort of counterintuitive patterns in management and how we manage these arid systems.
Yeah, so soil health has become a term that appears on a lot of packaging and in a lot of policy documents. Is there anything the phrase has come to mean in public that you'd really push back on?
I think that, yeah, it's a great question, and it does often get lumped in with terms like regenerative or sustainable, and I think that's we're all trying to get at the same thing: is how do you improve the functioning of soil, and ideally from the farmer's perspective, how can if you improve soil health, ideally that means you don't have to add as many external inputs like fertilizer and water which can be limiting resources and also cost a lot of money. I think where I think I keep some healthy skepticism and pushback is that soil health always means more crop yield, for example, or that it always means healthier food. Or so I think that we need to test these assumptions in a really systematic way. So that would probably be the thing that jumps to my mind right away is that we can't always assume a link between soil health and crop yield.
Yeah, so on a scale from 1 to 5, 5 being the most urgent, how urgent do you think the state of soil or soil degradation is? I'd like, yeah, just the number, the specific number first, and then why specifically.
Sorry, I think I'm going to give a typical response for a scientist in that the answer is it depends. And but to be more concrete than that, I would say that in if I were to break things like I've talked about, irrigated croplands and say more naturally or less intensively managed systems like rangelands, which are a majority of the land in the Western US. So with irrigated croplands, I would say honestly, if there is enough water, things are working really well. And I would say I'll give it a 2 on urgency scale. The big caveat is that in years like this, where you've probably heard that we have historically low runoff from snow, it was a really dry winter, which is where snow water is the main source of water in the Colorado River, things can go from a 2 to a 5 in 1 year. And it's not even always the water scarcity, it's the water quality issues that all of a sudden there's a lot of salts that build up in the soil. And is it this phrase that I've heard before that E. coli, for example, and that's very relevant now with food safety issue, E. coli kills people, salts kill civilizations. And there's examples from the past where societies that did not properly manage their salts cease to exist. And there's examples of that in ancient Mesopotamia versus Egypt. There's indigenous cultures in the southwestern US that face that issue. And as soon as we start running out of water, degradation can occur very quickly because there's not enough water to move those salts out of the soil profile. In more natural, say less managed, it also depends, but I would say it's more like a 2 or a 3, where there are lots of examples of, as I mentioned earlier, bare soils and changes in plant communities that, and particularly loss of plant cover, that is really increasing erosion rapidly. And I think that's, or where there are croplands that no longer have enough water to sustain food production or whatever crop they were growing that become abandoned and they don't really recover. As I like to say in Virginia, where I grew up, you could do just about anything to the soil, but and then if you just left it alone, it would recover. Whereas because there's enough rain and enough action going on, whereas here, if we have a drought after degradation, it can be very difficult for that ecosystem to recover.
Yeah, so who are a few scientists or thinkers who you think I should interview after you?
One person that comes to mind is I mentioned the work being done by my colleague's name is Laura Norman, and she works with the USGS based in Tucson. And she's really a champion for these, she calls them NIDS, NIDS, which is short for Natural Infrastructure and Dryland Streams. And these are the structures I mentioned that are meant, she likes the term be the beaver, or we had a lot more beavers on this landscape before they were hunted. There are still some examples, but I think that's a really a neat example of using natural processes to really try to emulate nature and restore. Let me think of a another person as well. I think a really another great person that would be good to talk with is a colleague here at the University of Arizona named Albert Barbaran, and his last name is spelled Baberan. And he is a great example of an ecosystem genomicist. Really, he does a lot of metagenomics and really tries to not only understand the microbial community, but how to link who's there with what they're doing, which is a long-standing issue in ecology, is how to link the structure of microbial communities to the functioning of microbial communities.
Yeah, and if you have anyone else, obviously I'll send you an email after the
Great.
interview and whatnot with some more information. So I have a few questions, two more. For a teenager who wants to take soil seriously, what's one thing that they could notice or do this week?
I think the great thing about soil, unless you're like only like swimming in the ocean, is that it's everywhere. You can find soil in your backyard, on your way to school. It's something that is really accessible. And I think that literally digging in your backyard is a great place to start. And it's really where my love of soil started and the clay rich soils of Virginia. And I think to be more concrete, that is to dig a hole and just start to observe. I think if somebody's really into birds, it's easy to go to maybe a place, a lake or a stream or somewhere where there's a lot of birds, and you just sit and observe. And I think we can do the equivalent of that in soil, is to dig a hole as deep as you can get and just make observations about what are the changes in color, feel the soil, smell the soil, what differences do you notice with changes in soil depth. You can buy a cheap soil test off of Amazon or your local nursery, and to get an idea of what is the relative nitrogen, phosphorus, potassium availability in the soil? How does pH vary? And then starting to understand what does that mean for the plants that are growing on your landscape. And then I think, honestly, it's easy to take a soil and you add water to it, make a nice dilute solution, put it on a microscope and look under it under a microscope. And I think really having an appreciation for the different sorts of organisms that are living in soil. For example, you'll probably see mites and nematodes and other organisms. And I think that's really a place to start to appreciate the biology of soil, which is really what got me into soil science. It was through biology and realizing that dirt is something that gets on your pants. Dirt is dead. Soil is alive. And I think really trying to appreciate the abundance of life in soil.
Yeah, so one more question. I ask this to all the scientists. I get very varied answers for this. And it's if you have one sentence to say to the next generation, what would it be?
Oh, that's a tough one to narrow it down to one. I think if I narrowed it down to one thing, it would be to practice doing hard things, to get out of our comfort zone. I would say very similar to it would be easier for you to not do these interviews. This is a hard thing to do, right? To go out of our comfort zone. And I'm a parent as well. I have 7-year-old twins. And my biggest wish for them is to be resilient, right? Not to be like a bulldozer parent called, right? That removes all obstacles in their kid's life, but to actually have to face challenges, to actually put yourself in hard, uncomfortable situations and to practice doing that and to fail and continue to try again, to continue doing those things again. So I think really doing hard things, and that really depends on what is hard. Some people are really good at talking with people, for example, or asking questions, whereas for other people, that might be the hard thing to do is to actually go up to a person or a scientist or somebody that's doing their dream job and ask them, what do you recommend? And that's something I actually have my classes do, and they get a lot out of it, is understanding what skills are needed for your dream job.